Hi everyone, welcome to section 11.3. This is Nick Jacobs, your intermediate algebra instructor here at Yavapai College. Today we're going to continue on with quadratics. We have seen graphing different quadratics. We have translated them both vertically and horizontally. Today we're going to talk about quadratic equations. So let's get started. We're going to kind of continue on some of the same aspects of 11.2, but we're going to look at different, just learning the basics of quadratic equations. We're going to solve them using the square root property. We're going to continue on completing the square. And then we're going to solve an equation for a variable and then do some applications of quadratic equations as well. So some basics of quadratic equations. Now, you guys all know this already from past sections, but we know that any quadratic function f can be represented by f of x equals ax squared plus bx plus c, with a not equal to 0. Again, this is the standard form of a quadratic. So some examples here would be 2x squared minus 1, negative 1/3 x squared plus 2x, x squared plus 2x minus 1. All three of these have an x squared term, and that's the largest variable term or the highest degree term, as we say. So those all have a degree of 2. And again, we know that the standard form of a quadratic is this guy, the ax squared plus bx plus c. Okay, so now what we're going to do here today mostly is learn about different types of solutions of a quadratic equation. So solutions to a quadratic equation are where the quadratic touches or crosses the x-axis. So a quadratic, right, is a u-shaped function, right? It may have something that does not, so it may be a function that does not touch or cross the x-axis. So in that case, in this case, our first case, this would have no x-intercepts, so it has no solutions, okay? We have another case where the quadratic would have one x-intercept, or it would just touch the x-axis one time, and that would have one solution, okay? So this one, it would have no real solutions. Okay, this one, it would have one solution, okay, where it just touches the x-axis. And then this one crosses the x-axis in two places. So that would have two solutions, or two, we should say, real solutions, okay? And I should really say one real solution. If it has no solutions, it would have imaginary solutions. We're not actually going to talk about that in this section, so you don't have to worry about imaginary solutions. We have talked about the concept of complex numbers and all that, but we won't talk about imaginary solutions for quadratics. They're either basically going to have no solutions, one real solution, or two real solutions. So let's go through some examples of quadratics. Okay, so what we're going to do here is we're going to solve each quadratic. We're going to solve it symbolically, we're going to solve it numerically, and then graphically. So you can kind of see what solutions would look like here, okay, or if it has any solutions. So our first quadratic here is 3x squared plus 2 equals 0, okay? And we want to know how we would symbolically solve that. So what you would do here is you would go about this and you would basically solve for x, or solve for x squared and then solve for x. Well, in this case, once we do that, so in this equation, we subtract 2 to both sides. So we get 3x squared equals negative 2, and then divide both sides by 3. So we have x squared equals negative 2/3. But when I would square root both sides of this, we notice that we cannot take a square root of a negative number. So this case symbolically has no real solutions, okay, because x squared needs to be greater than or equal to 0 for all real numbers x. So this has to be positive, basically, Okay. Now, numerically, okay, if we were doing that, and what I mean by numeric is we would make a table. Okay, so you can make a table that looks something like this. Pick your X values. Again, you can choose whatever you want, and then substitute those X's in for X, basically, and then you would get an output of Y. So instead of like 3x squared plus 2 equals 0, you'd have 3x squared plus 2 equals Y, and then you're getting outputs for Y. So when you plug in -1 for X, here you get 3 times -1 squared, which is 3. 3 plus 2 is 5. That's where we get the output there. Plug in 0 for X, you get an output of 2, right? 0 plus 2 is 2. So that's numerically what that would look like. And then graphically, this quadratic looks something like this. Okay, so if I were to plot those 3 points, really you only need 3 points when graphing a quadratic. But when you would do that, graphing those 3 points, it looks something like so. And notice that this quadratic does not intersect the x-axis. So this one has no real solutions, as we said here before when we figured that out symbolically. And you can see that in the graph. So let's go on to the next example. So we're going to solve this one. We're going to try to do it symbolically, numerically, and then graphically. So to solve this quadratic symbolically, what I need to do is I need to make it look like ax squared plus bx plus c. So what I'm going to do is I'm going to add the 6x over to the other side. So I have x squared. I'm going to add 6x over to both sides. That's going to zero out the right side. And then I have plus 9 equals 0. Okay. Now I notice that this is one of our perfect square trinomials. Okay. And we will talk about later how to complete the square when this is not a perfect square trinomial, right? We're going to have to make it into a perfect square trinomial like we talked about last time. But this one is. So what does that mean? That means that this is equal to x plus 3 squared. And what I can do here really is, this is x plus 3 times x plus 3, right? So really here, using the zero product property as we've used in the past, we just basically take each of these things and we set them equal to 0. So either x plus 3 equals 0 or x plus 3 equals 0, same thing, right? So either x equals -3 or x equals -3. Well, it just has one solution. Okay, so this equation, okay, or this quadratic, so the equation, I'll just say, again, we could call it a quadratic. Could also call it a parabola. I've been calling them quadratics so far, but a parabola, right? We could call it that. The equation has one real solution, right? And where is that solution? It's at x equals -3. So this should be a parabola or a quadratic that crosses, or actually doesn't cross, but it touches the x-axis at the point -3, 0. And when we graph that, that's what we should see, okay? So next we're going to make our XY chart. Well, I did this because why? Well, because this should be our middle point, right? So it should be -3, 0. So if you took this equation, right, and you had that y equals x squared plus 6x plus 9, and you plugged in -3 for x, you should get 0 here. So -3 squared is 9. 6 times -3 is -18, and then we bring down the 9, and y does equal 0 here again, where x equals -3. We substitute that. If I substituted -5 for x in this equation, I would get 4. If I substituted -4, I would get 1. And then these are just going to be the same thing, a 1 and a 4. So this is actually going to look like, and you can use Desmos to verify, you would just graph y equals x squared plus 6x plus 9. To verify this graph, this is going to look something like this. Okay, 1, 2, 3, 4. And 4 over here. So that's what this parabola or quadratic looks like. Okay. Again, it has one real solution. It touches the x-axis at the vertex -3, 0. And by the way, we kind of learned our vertex form last section, right? So we could have taken this standard form and turned it into vertex form, right? Well, this is your vertex form right here, x plus 3 squared equals 0, basically. Okay, where remember your vertex is at the point h, k. Well, remember our vertex here of h, right? And we had this form from last section. This is what it is basically right here. It's x plus 3 squared plus, well, nothing, right? 0. There's nothing over here. So then this would have a vertex again at -3, 0. So it makes sense. And then the last example here, this one you can guess is going to have 2 real solutions. So let's figure that out. So we have x squared plus 2x minus 8. Again, I can actually factor this. So we know factors of -8 would be that add to 2 would be 4 and -2. So this would be x plus 4 and x minus 2. Okay. And so the solutions are when you set each of these equal to 0 using your 0 product property. That's solutions of the quadratic. So either x plus 4 equals 0 or x minus 2 equals 0. So your 2 solutions would be x equals -4 or x equals 2. Again, those are points, -4, 0, and then 2, 0. So those should, so this quadratic should have a point here at 2, 0. And then it also should have a point right here at -4, 0. And what we're going to do here, well, let me just state here that the equation, or again, the quadratic / parabola, has 2 real solutions. That's what this means, okay? When we solve it and we get x values that work, okay? At x equals -4 and x equals 2. Again, you could say that that's -4, 0, and at 2, 0. Okay. But again, what you could do is you could make your table. Okay, I chose -4 and 2 are definitely going to be in there because those should be equal to 0. And if you plug those in, right, to our original equation, you would get zeros for those. And then you can just figure out some other points here. So I kind of, gave these 3 points because this is going to make our quadratic look really nice. But so when you plug in -2 here, we get -2 squared plus 2 times -2 minus 8. That's going to be 4 minus 4 minus 8. So that's going to be -8. -1 squared is 1 plus, let's see, -2 minus 8. So that's going to be -9. And then this one, if we just plug in 0, well, 0 plus 0 minus 8 is -8. So I'm going to have points here at -2, -8, 0, or sorry, -1, -9, and then 0, -8. So this parabola quadratic is going to look like so. Okay. And it makes sense. It's opening upward, and it makes sense that it's opening upwards because your a value was a positive, right? We learned that last, actually the last 2 sections. And then also, I guess another thing, remember when we learned about the axis of symmetry, right? The axis of symmetry was -b over 2a. Well, you could even take this here, right? Our b value is 2, so we have -2 over 2 times a. Well, a is 1. So then an axis of symmetry for this should be at -1, and it is, right? It is. Remember our axis of symmetry, that dotted line that we learned in 11.1. And our vertex down here of -1, -9, you could also check that kind of as well. Well, actually, we haven't learned as far as the vertex. Well, we did learn that it is the axis of symmetry, right? The x value for that of -1. And then if you know that, then you just plug in -1 for x, and that would give you your y value of your vertex. So you have learned that, okay? So that is what that one looks like. Again, this one has 2 real solutions because it crosses the x-axis in 2 points. You're never going to have a quadratic with 3 real solutions, right? Because a quadratic is always U-shaped. It doesn't have another like third line or whatever. Okay, now let's learn some other properties of solving quadratics, okay? So sometimes we don't have a middle kind of x term, and that's when we have to use this square root property, okay? So if you have this, okay, if you have a non-negative number here is equal to an x squared, then solutions are given by x equals plus or minus the square root of that thing, okay? So again, if you have x squared equals k or something like that, what you would do is you would square root both sides, and then you would get solution, one is positive square root of that thing, and one is negative square root of that thing. If k is less than 0, then that equation is going to have no real solutions. So that would be when you're trying to take the square root of a negative number. So let's go through, some examples here. I had that one up there down below. So I have 4 different examples. We're going to solve each of these. I just added this last one in because it does equal a negative number. But again, if you have something, so here we have no kind of middle x term. So what we do is we get the x squared term on one side, get everything else on the other side. And once the x squared term is alone, then we square root it. So this is already alone. So what I do is I just take the square root of both sides, okay? And when I do that, I have to take plus or minus this thing, okay? Because it could be that it is positive or negative, right? If I have a, if I'm squaring a square root, this can be positive or negative, right? Because if I have x squared equals 25, well, x could either be equal to -5 or it could be equal to +5, right? We've talked about that in previous sections. So you have to consider both the positive and the negative square roots. And so that is just your answer. X is equal to positive square root of 10 or negative square root of 10. You could write that out as 10 or square root of 10 or negative square root of 10 if you want, okay? That's what the plus minus means. One's positive, one's negative. So again, this one has no middle x term. So what you do is you try to get x squared alone. So I'm going to add the 16 over. I have 25x squared equals positive 16. I divide by 25. So I have 16 over 25. And at this point, because our x squared term is alone, I can square root both sides. So I square root the x squared and I square root the 16 over 25, making sure to make it a plus minus. And so you have solutions of x equals plus or minus square root of 16 over 25, which is really square root of 16 over 25 is 4/5, right? We had that property where we could break this guy up. So either x equals 4/5 or x is equal to -4/5. Okay, so if you graphed this quadratic, you would have a parabola that crosses at 4/5 and -4/5. Same thing with this one. You'd have a parabola that crosses at the square root of 10 and negative square root of 10. Okay, another example. This one is x minus 3 quantity squared equals 16. So in this case, it is already just an x squared term. This whole thing is squared. So we can just square root it to get that alone. Okay, so I'm going to rewrite it. And I'm going to square root this again, taking plus or minus the square root of the other side. So it'll be x minus 3 equals plus or minus square root of 16. And then in this case, I have the 3 left over. So I'm going to add it to the other side. When I do that, I write it in front of the square root. There are some reasons I do that. But for now, we know that The square root of 16 is 4. And so one of your solutions would be x equals 3 plus 4 or x equals 3 minus 4. So really x is equal to 7 or x is equal to -1. Okay, and I'll just box. I'll box all these that I've done so far. So those are examples of your square root property. Again, when you don't have that middle x term. This guy is equal to, x squared is equal to -10. So if I tried to take the square root of a -10, well, I can't do that, right? I would have to use an imaginary number, and we're not going to use imaginaries quite yet for this. So I can't take the square root of a negative, so I'd have no real solutions for this example. All right, let's do some applications here. So let's do a little bit of a real world connection here on an actual problem. So here's a formula that I'll give here. So if an object is dropped from a height of h feet, its distance d above the ground after t seconds is given by d of t equals h minus 16t squared. This is actually a general equation often used in physics and whatnot. But let's try to figure that. Obviously, physics has more applications or more involvements when you talk about gravity and things like that. But this is just a general equation. So if a toy falls 40 feet from a window, how long does it take for the toy to hit the ground? Okay, so you have, you could have this, this taller type of building right here. You have let's say this window. Okay, you have a toy that's on the window and it falls to the ground. Okay, and this distance right here is 40 feet. Okay, we want to know how long it takes for the toy to fall to the ground. So what you can do is you can use this formula that I just gave you. Okay, so the distance d of t, and we can go back if you don't remember what that means. Okay, it's the distance d above the ground after t seconds. So the distance d above the ground after t seconds. So we don't know how many seconds, right? But we do know the height. We do know 40 feet. So h is representing the height in this case. So what I do is I plug in 40 for h. Okay, so I have d of t equals 40 minus 16t squared. Okay, now this is looking like it's going to be one of those square root property problems, right? Because I have no t value. I just have d of t. Well, what is d of t? Well, d of t in this case is just 0 because I don't know it. I don't know it yet, right? The distance above the ground, or sorry, I need to look back sometimes. D of t is the distance above the ground after t seconds. Okay, I don't know that, right? Well, I know that it's 40 feet above the ground, but this is just a formula, right? So what I do here is I set this equal to 0, basically. Okay, so this is 0. And then what I'm doing here is, let me actually turn this around. I'll just leave it. I'll leave it like this. So what I'm doing here is I'm solving for the time. Okay, I'm solving for the time. So I need to know how long it takes the toy to hit the ground. Okay, its distance, d of t, I should say, above the ground, when it hits the ground is 0. It's 0 feet right here above the ground. Okay, that's why this is 0. I said it was 0 before, just because it's 0 because it's 0 feet above the ground when the toy hits the ground. Okay, that's why you make this 0. And when we solve for t, that's gonna tell us the time it takes for it to be 0 feet above the ground. Okay, so let's go ahead and do that. So we need to isolate t. So we need to get t alone. So what I'm going to do is I'm going to first subtract 40. So I'm going to have negative 40 on this side when I subtract it equals negative 16t squared. Divide by negative 16, that's going to make this a positive 40 over 16 equals t squared, okay? Actually, what I'm going to do at this point is I'm going to turn this around so it looks a little bit nicer. So I have t squared equals 40 over 16. Now I square root both sides, okay? So I have t equals plus or minus the square root of 40 over 16. And then what you do at this point is you're going to keep simplifying this. Actually, instead of saying equals, sometimes that confuses people. I'm going to continue on with this problem by doing this, plus or minus the square root of 40 over 16. So we learn in another section, right, that you can separate this into square root of 40 over the square root of 16. And I know that the square root of 40 is going to simplify into the square root of 4 times the square root of 10. And the square root of 16, I know what that is, right? So I have, t equals plus or minus 2, right? That's the square root of 4 times square root of 10. All over square root of 16 is 4. Now, when I have something like this, I can actually simplify it. I can simplify this fraction. So I can make this into 1/2. So 2/4 is the same thing as 1/2. So I really just make this as 1, and 1 times the square root of 10 over 2. I don't really need the 1 in there, so I can just write the square root of 10 over 2. Now, if you take this guy, the square root of 10 over 2, and you put it on your calculator, okay, you're going to get for the square root of 10 over 2 that's about 1.6. It's about 1.6. And for this guy, negative, that one, I actually didn't calculate that. There's a reason for that. But that one is going to be about negative 1.6. Negative 1.6. Yeah, about negative 1.6. Okay. Now, what's the problem with that? Well, the problem is that you can't have a time that's negative. Remember, we were solving for the time. So here, the time is going to be equal to positive 1.6 seconds. So what does that mean? It takes the toy 1.6 seconds to hit the ground. Okay, 1.6 seconds to hit ground. That's what it means. Okay, and again, we don't use the negative one because can't have a negative time. But this quadratic would actually kind of look like, something like that, right? But again, if it has a vertex, right, the vertex would kind of be up here by the window, right? The toy is just falling. So actually it kind of have it looks like the vertex is up here a little bit. I kind of just drew it wrong. It would actually just go down right away. Okay, and your vertex would be here at the window. But again, we can't have a negative time, so we only use the positive. So 1.6 seconds. All right, now the next part of this section is completing the square. So more on completing the square. So if you're watching, I would just, take a break. We have a lot to work on for the rest of the video. So let's get to it here. If you paused it and you kind of came back. So completing the square. So we want to find the term here that should be added to x squared minus 8x to form a perfect square trinomial. Okay, and we talked about this last section. Okay, so recall, I'll say recall from section 11.2. Okay, what is that term that allows us to form a perfect square trinomial? Well, that term is b over 2 squared. Okay, is that term. Okay, find the term that should be added to x plus 2, or sorry, not x plus 2, x squared minus 8x to form a perfect square trinomial. Okay, so x squared minus 8x, okay, plus, right, added to this is this b over 2 squared term. Okay, now what is b over 2 squared in this case? Well, we know that, so what do we know? We know, well, we know a lot of things, right? But we know, hopefully you do, that our standard form of a quadratic is ax squared plus bx plus c. Well, in this case, our quadratic is equal to x squared minus 8x. So what does that tell us? It tells us that b is equal to what? B is equal to -8. Okay, so if I'm trying to do b over 2 squared, I'm doing -8 is our b value over 2 squared. -8 divided by 2 is -4, and squaring that is 16. So what term do I add to x squared minus 8 to make it a perfect square trinomial? I add 16. Okay, I add 16. Okay, that's going to make this a perfect square trinomial. And we also learned last section that when you complete the square, now this example does not tell you to complete the square, it just asks you for the term. But when you complete the square, you not only have to add that term, but you have to subtract it. Okay, you add it and you subtract it. And we'll get into examples of that, specifically where we have a quadratic equation now, where it's equal to 0. Okay, now last section, it wasn't equal to 0. Okay, so we just added it and subtracted it right away. This time we're gonna add it basically to both sides, right? And I'll show you an example of that here. But another way to write this guy, right? This is a perfect square trinomial, would be x minus 4 squared, right? So x squared minus 8x plus 16. I could also write that as x minus 4 squared. Again, x minus 4 squared means x minus 4 times x minus 4. When you FOIL all of this out, you're going to end up back where you started at x squared minus 8x plus 16. So you should get that. And you can check that if you're not sure if this is correct. Here are some steps to completing the square in any quadratic equation. Now this uses a little bit different basically variables, okay, where they have d being b over 2 squared. They just give that value as a d there, but you kind of get the idea here. And if you think this is helpful for you, you can definitely use that. I'm not going to go through all this, but instead I'll show you guys an example. So I was going to go over a similar example to what we did last section, but I actually made up a equation for this one. So we're going to solve this equation, x squared minus 6x plus 4. Again here, an important thing to note is that a is equal to 1 in this case. Remember, we have our standard form. Okay, you always want to check the value a, the constant in front of x squared. Okay, this is an a. Let me just erase that. Okay, let me erase this. You always want to check what a is equal to. If it's equal to 1, we're golden, we can keep going. If it's not equal to 1, we have to do a little bit of work first, and I'll go through an example on that. But let's solve this equation. So you can obviously tell here, hopefully, that this is not a perfect square trinomial. Well, it is, I mean, both of these are perfect squares, x squared and 4. But I still can't factor this, right? Because if I did take 1 times 4 as 4, well, there are no factors of 4 that add to give me a -6. So what I have to do is I have to complete the square, okay? So what do? Well, first of all, let's do this. Let's find, since I know I have to complete the square, let's find our b squared over 2 term. So first of all, what is b in this equation over here? Well, b is -6, right? You know, it's the coefficient next to x. And then b over 2 squared would be -6 over 2, right? Squared, which is -3 squared, and that equals 9. So when I do that, and I'm going to show you where I use this here in just a second. So when I do this, what I want to do is I want to have this x squared minus 6x, okay? And I'm going to actually, as I move the 4 over to clear a space for this b squared over 2 term, and that's going to go here and here. So this 9 value, right, that I got from b over 2 squared is going to go here, right, plus 9, and it's also going to go over here, plus 9. So I didn't change this equation at all, right? I took this 4, I moved it to the other side, and then all I simply did was added 9 to both sides. So this equation is still the same thing as I started off with, but I'm completing the square in order to get a perfect square trinomial. So on the left here, we now have a perfect square trinomial. And that's what I want. Okay, I need this to be a perfect square trinomial so that I can easily factor it into something plus something squared or something, or x minus something squared. So it's going to either be x plus something squared or x minus something squared. Well, in this case, it's x, you tell me, x minus 3 squared, right? And that equals 5. Okay, negative 4 plus 9. So I add 9 to one side, I add 9 to the other side. One side is now a perfect square trinomial. The other side is just this constant 5. And now what I do is I keep solving. So originally I wanted to solve this, right? So I'm solving it for x by completing the square. Okay, so I'm solving for x by completing the square. There's other ways that I could solve for x. I could use the quadratic formula, which I'll talk about next section. But now we're learning about how to complete the square. And the whole purpose of learning this is to connect it with your graphing of quadratics, right? To connect it with that vertex form, okay, which is kind of where we started this in last section, okay? So now let's continue. And when I have this, this is our square root property, okay? So now this is going to be our square root property, where I have a square term on one side, I have another term on another side. So I'm going to square root both sides of this equation. And when I do that over here, I still need the plus or minus. Okay, I still need the plus or minus. Let me erase that so you can clearly see here that this equals plus or minus the square root of 5. So when I square root this side, I get x minus 3, right? When you square a square root, right? Or when you take a square root of a square, you're going to get what's on the inside, x minus 3, and that equals plus or minus square root of 5. Now I add the 3. And I always put that in front of this. So it's 3 plus or minus the square root of 5. So then again, one term is x equals 3 plus the square root of 5, or the other term is x equals 3 minus the square root of 5. And you could take those and figure them out on your calculator. This is the exact answer, and this is the approximate answer when you do it on your calculator. So this one is 3 plus the square root of 5. Let's round it to the nearest hundredth. That's about 5.24. And this one is about 0.76, rounded to the nearest hundredth. So this is the exact answer. So on your homework, if it asks you for the exact answer, you would include the radical, okay? If it asks you for the approximate answer, you would round it to whatever they want you to round it to, okay? So that's an example of completing the square when a is equal to 1. Now, let's go to an example where a is not equal to 1. So I did this one for you, or I made this one up. I have 0 equals 3x squared minus 6x plus 2. Now, to start this off, I'm going to make this look a little bit better. I just like, for me, it's better to just have the 0 on the right side. But we notice here that a is not equal to 0 in this case. In fact, a is equal to what? A is equal to 3. Okay, so what I have to do here, the last section, kind of what I did is I factored it out. And that's definitely one way you could do it. The other way is you could kind of divide it off. Okay, you could divide it off, and I'll show you what I mean. So I'm going to start it the same way. I have 3x squared minus 6x. I'm going to move the -2 over to the other side. Okay. But in order to complete the square, in order to find this b over 2 squared term, this has to be a 1. So I have to make this a 1. And I do that by dividing everything by the a term. So I divide everything by 3. Or not the a term, but the a coefficient. So I divide everything by 3. So if this was a 5, I would divide everything by 5. If this was a 1/5, I would divide everything by 1/5. Okay. So this is going to be x squared minus 6x divided by 3 is 2x. And that equals -2/3. And now what I can do is I can find that b squared over 2 term because my leading coefficient is a 1. So I'm going to find the b squared over 2 term, and I'll just do it in red here. Okay. Or sorry, not b squared over 2, it's b over 2 squared. And if I said b squared over 2, I'm sorry. But it's b over 2 squared. What is b? Okay. B is this value. It's the -2. Okay, that I found after I divided the 3. So a very common mistake is people would take this right away and then go, oh, b is -6. Okay, that kind of makes sense. I see where you're coming from there, but you have to do it after you divide. So your leading coefficient has to be a 1. So let's go ahead and plug in -2 for b. So I have -2 over 2, and then I'm going to square that. So -2 over 2 is -1. Squaring that, I get -1 squared, which is 1. So my b over 2 squared term is 1. So I'm going to add 1 to both sides. So now I have x squared minus 2x plus 1 equals 1/3. That's -2/3 plus 1. And now this is my perfect squared trinomial. So this is x minus 1 squared. If you don't believe me, FOIL that out. You'll get this guy, x squared minus 2x plus 1. And now that I have that, I'm going to use my square root property, just like I did last time, and I'm going to square root both sides. Again, on the right side, you've got to take plus or minus that thing. Okay. And I'm going to get x minus 1 equals the plus or minus the square root of 1/3. I have to add 1 to the other side, so I get x equals 1 plus or minus the square root of 1/3. So again, here, either x equals 1 plus the square root of 1/3, or x equals 1 minus the square root of 1/3. Again, this is your exact answer. And your approximate answers, would be x is about, again, we'll go to the nearest hundredth, 1.58, or x is equal to 0.42. Again, these have two real solutions. Okay, and that's where they would cross the x-axis. Again, the difference here in the questions is that this one had a leading coefficient of 1. I didn't need to divide anything. I just kind of went right into the completing the square method. And then this method, I had a leading coefficient of 3. So I needed to divide that off from every term in order to get it down to an x squared or a leading x squared term without another coefficient besides 1. All right, not too much more, but what I wanted to do here is I have this equation here, this w equals 16x squared. And what I'm going to do here is I'm going to solve for the specified variable. So they want us to solve this for x. So I just wanted to show you this quick example here. So again, I like to have the x squared term on the left. That's just me. If you don't care, that's fine. But what I need to do here is, again, I want to solve for x, so I need to get the x squared term alone. So I can't have any coefficient out here. So what I do is I divide both sides by 16. So I have x squared equals w over 16. Again, you're going to use your square root property. So you square root both sides. When you do that on the right, you have to still do the plus or minus. And so one of your answers is the square root, or sorry, plus or minus. Actually, I'm missing a step here before I do that. I know what the square root of 16 is, right? So when I do this, I can actually break this up and do the square root of w divided by the square root of 16, which is equal to plus or minus the square root of w over square root of 16 is 4. So really I have x equals positive square root of w over 4, or x equals negative square root of w over 4. And that is your solution. Those are your two solutions for that case when you're solving for that specified variable. All right, I have one final application problem here. This one is on the use of the internet. So sometimes they use quadratics to model things like this, okay? If you think about internet usage early on, it grew very, very rapidly, okay? So it's an exponential, okay? It's a quadratic, basically. It's an exponential function. So this shows the use of internet in Western Europe over how it increased when it kind of was first starting up here in the 90s. So here's a function that models that data. It's f of x equals 0.976 x squared minus 4.643 x plus 0.238, okay? Now, the important thing here is that the output is in millions, okay? So the output is in millions, and it even gives you that here in the graph, okay? And then another important thing here is that x equals 6 corresponds to the year 1996. Okay, so year 7 would be 97, 1998, 1999. 10 would be the year 2000, 2001. 12 would be 2002. Okay. And they don't show us how many users there were in year 13 or 2003 here, but you kind of get the idea. So what we're going to do here is we're going to evaluate f of 10. Now, what does that mean? Okay, let's just look at the graph before we go on. F of 10 means how many million users were there, or how many million users were there in year 10, or the year 2000. So that would be this dot. Well, we don't really know exactly what it is based on that dot. So what we would do is we would plug in 10 for x, and we would get an answer, okay? So let's evaluate f of 10 and then interpret that result. So what I'm going to do here is I'm going to take my formula up here that they gave us, and I'm going to plug in 10 everywhere that you see an x. So f of 10 equals 0.976 times 10 squared minus 4.643 times 10 plus 0.238. And if you type all this in on your calculator, round it to the nearest tenth, you're going to get about 51.4. Now, what does that mean? Again, since x equals 10 corresponds to the year 2000, this means that, there were about 51.4 million internet users in 2000. There's way more than that now, right? There's billions of them, right? But that's kind of what this means. That's that interpretation. Okay, now part B, I kind of want you to graph this, okay? And if you want to use Desmos, you can, but I'll just kind of show you quick and wrap it up here. but we're going to estimate the year in which the number of internet users reached 85 million. Well, actually for this one, if you go on your graph and you kind of look here, 85 million. Well, it looks like 85 million is right about here. So right about year 12 or year 2002. Okay. So if you graphed it, oh, did I? Maybe I don't have the graph. Let me go ahead and let me do that here. Keep those. I'm going to go into Desmos. Okay, and let's just graph this. Hopefully you can see up. It said my screen sharing is paused. I'm going to share Desmos. So I'm on Desmos now. So I have 0.976x squared. It's a parabola, of course, because it's an x squared, minus 4.643x, and then plus 0.238. And what they wanted to know was estimate the year where the number of internet users reached 85 million. Well, I would need basically the year that it reached 85 million. So I would need where this is 85. Okay, where this parabola is at 85 over here. And it looks like 85 right about here. And yeah, so it looks like somewhere around 12, right? Actually 85.01 is 11.997 for X, and X was the years, right? So I think what you can do actually in Desmos, I just lost it. You could actually type in, when X equals 12, what does this equal? And I don't actually remember how to do that on here. I'm trying to click on some of the settings. Convert the table. Oh, here we go. What about if I type in 12? There we go. So if I type in 12 to my table, it's actually 85.066. So a little bit more than 85 million, but we kind of get the point that in year 12 or the year 2002, there were about 85 million users. So you kind of learned a new thing here. So what you would do is, you'd have a formula and you can actually convert it to a table. And then part C was solving that numerically. I'm not going to do that, but you kind of get the idea there that the whole point is year 12 there, or 2002, there were 85 million users, internet users. So that is section 11.3. I know these sections of chapter 11 have been long, but they're really important. And there are only 4 sections in chapter 11. So some of the other chapters we've had 6 sections, I think, maybe even more than that. I think chapter 6, we had 7 sections. So I know these are a little bit longer lectures, but there are only 4 sections. So hopefully, that can give you a little bit better peace of mind, I guess. But we'll see you next time for section 11 for the last section in the chapter. So have a good one.